This video is for topic 7.11, Introduction to Solubility Equilibria. The objective for this topic is to calculate the solubility of a salt based on the value of KSP for that salt. So all solids dissolve to some extent. Up until this point, we've pretty much considered salts as soluble or insoluble. So they dissolve or they don't. But really, all solids are in equilibrium. So if we say that they're soluble, they just have a really high K value, which means that they greatly favor the ions or the product over the solid. Or if they have a very small K value, that means they favor the solid over the ion. So they favor the reactants over the products. We call this KSP when we talk about the equilibrium, which is for the solubility product. It's calculated the exact same way. I realize that there is a typo on the slide. Instead of aqueous in the reactants, it should be solid. I don't know why it says aqueous. Typo. But solids aren't included in equilibrium expressions. So we're only going to include the aqueous ions, which are the products. And so the KSP expression is written the exact same way. It's the concentration of each ion raised to the power, that power being their corresponding coefficients. So since we don't include solids in our equilibria expressions, the reactants aren't included. So it's just products. So in this question, we're looking at the solubility of calcium fluoride. So it dissolves a little bit in water, and we want to know to what extent. So the KSP value will tell us or give us an indication of to what extent it dissolves. So in this sample, the calcium ion concentration is 2.3 times 10 to the negative fourth. So that's given to us in the problem. And then we know from our reaction stoichiometry that it's a 1:2 ratio. So if our calcium ion concentration is 2.3 times 10 to the negative fourth, our fluoride ion concentration is going to be twice that, because the concentration of fluoride ion is equal to 2 times the concentration of calcium ion. So that's coming from our stoichiometry. That's coming from the ratio of the fluoride to calcium ions in the calcium fluoride compound. So this gets us 4.6 times 10 to the negative fourth for our concentration of fluoride ion. Now, our KSP expression is going to just include the ions because our equilibrium never includes solids. So the only reactant we have is a solid, so it's just going to be our products. So it's going to be the concentration of calcium ion times the concentration of the fluoride ion squared, again because of the coefficient of 2. So then we're going to plug in our concentrations. And that gets us a KSP value of 4.9 times 10 to the negative 11th. So this is not very soluble at all. It's definitely an equilibrium that prefers the reactants, which in this case is the solid. So this question has us looking at the mineral barite, BaSO4, barium sulfate. And we are told that the KSP value is 1.1 times 10 to the negative 10th at 25 degrees Celsius. The question asks us to calculate the solubility of barium sulfate in pure water in 2 units, moles per liter and grams per liter. When it asks us to calculate the solubility, what it wants us, especially when we're given the KSP, what it wants to know is the concentration. Okay, so it wants to know what the concentration of barium sulfate is, in this case, in terms of 2 units, moles per liter and grams per liter. So the first thing we need to look at here is an ice table, essentially. So we know that the reaction would be barium sulfate, so BaSO4, as a solid, breaking apart into its two ions, which are barium and sulfate. Now, since we don't include solids in our equilibrium expression, we're only going to focus on our products for our ice table. And initially, there aren't going to be any products, so we start at 0. And we know that they're going to go up by some amount x. They're in a 1-to-1 ratio, so the coefficients are 1. So at equilibrium, the concentration is equal to x. This means our equilibrium expression, or our KSP, would be x times x, because it's the barium ion times the concentration of the sulfate ion, which is equal to x squared. So when we're solving for x, our KSP is 1.1 times 10 to the negative 10th equals x squared. To undo the square, you take the square root of both sides, and you get x to be a concentration of 1 times 10 to the negative 5th. Standard KSP concentration units are in moles per liter. So that's our first answer. So that's the answer to A, because our standard concentration units are molarity, so moles per liter. Now B asks us to convert that into grams per liter. So we're just going to do a quick mole to gram conversion. So we know we have 1 times 10 to the negative 5th moles per liter. For barium sulfate, the molar mass is 233.39 grams per mole, which gets us 0.0023 grams per liter. So that would be our answer to B. So one last note about solubility equilibria is that if you have salts with the same cation to anion ratio, so this is often common when you have the same metal cation and different anions, but when the ratio is the same, so 1-to-1 or 1-to-2, you can make direct comparisons between the solubilities. So that means a larger KSP is going to be more soluble, a smaller KSP is going to be less soluble. So if we compare our silver iodide to our silver bromide to our silver chloride has the highest KSP, although it's still incredibly low, but it has the highest KSP of the three, therefore it is the most soluble of the three, and the silver iodide, which has the smallest KSP value, is the least soluble of those three. And then likewise, we can compare with lead-2 iodide, lead-2 bromide, and lead-2 chloride. So lead-2 chloride has our highest KSP value, also still very small, so it's still relatively insoluble. And then lead-2 iodide has our smallest KSP, which means it is our least soluble. So if they're the same ratio between the metal and the nonmetal, you can compare their KSPs to talk about their solubility.